That's the magic part. So I guess we'll get things going. There's a couple other stragglers, so we'll keep an eye on the door in case they show up. Welcome everybody. We have a really big group here tonight. I'm glad to see lots of new faces.
So the pressure's on.
Yeah, no pressure, Chris. We're going to give you a little introduction about what this whole workshop series is about. Simon is going to help with that. Right now I'm just going to give you a kind of a selfless plug for Astronomy Day, which is coming up in a couple of weeks on the 21st. It's a event that happens all over the world on the same day, and the purpose of the event is to promote an interest in astronomy and science in general. So the idea is for volunteers to come out to public events and share their love of astronomy with just passers-by. And there's two main activities in the Ottawa area. There's the public star party that happens at Silver City near the Chapters store there. Maybe you've seen it happen in past years. I'm the contact for that. And then there will be something at the Aviation and Space Museum, which is coordinated through Chris Terham. So if you want to participate in either of those to, either all day, be there for an hour or whatever, contact either of us, and it would be greatly appreciated. It's usually a lot of fun. Usually freezing cold and windy, but all the excitement from people never looking through a telescope before, it's totally worth it. So that's it for my selfless plug. Thank you.
Is Simon going to do something too?
Yeah, Simon is going to.
Oh, no, there he is. I got back.
While they're fiddling there with the technology, just a word of introduction or a reminder for those of you that have already heard this. What this series is all about is a combined presentation between the Royal Astronomical Society Ottawa chapter and the Ottawa Valley Astronomers and Observers Group. And the object of the exercise here is to actually present an adjunct, if you will, to the RASC initiative, Understanding the Universe. What do we mean by understanding? By understanding we mean it's a little bit more than simple stamp collecting. Simply thinking, well, I've got my list of objects I want to see, and I look through my telescope and I check them off and say, yes, I saw that. What we're looking at here is trying to give you a flavor of what's behind the understanding of what you're looking at. Now, in some cases, the science is way behind our own questions. And the answer to what do scientists think this is they don't know. But what we like to do is give you an idea of what it is they're thinking, or give you an idea of what they thought and they no longer think. Sometimes that can be a little frustrating because you walk away thinking, well, what exactly was the answer? Well, there isn't necessarily one yet. Each presentation is different. Some presentations will contain more science and some will contain more observations. But they're all about getting you to think about what is it that I'm looking at and what are other people thinking about this object or this series of objects. On that point, I'll give it over to Chris.
Me. Okay. Jim, can we just test the lights a little bit just to see? I'm going to try to work without the light if I can, but if we can maybe just dim it down a little bit more and I'll close this door a bit more.
I think the dimmers are just behind the screens.
Yeah,
Yeah, I'll need a little bit more. Good. Yeah, that's probably okay.
One more.
Can you see your notes well enough there, Chris? Or do you need
Yeah, well, yeah, I think I'll manage. It's better than having this headlamp on. It's a little brighter than what I.
Anybody?
I know you're coming to me, you're trying to find me.
Well, it's here.
Well, I guess I'll
Thank you,
get.
Steve. Thank you, Steve.
What's happening?
Pass them to the back.
Yeah, go ahead.
Leave, Chris, we can't do this without you.
So I'll get started. My name is Chris Tooman. Some time ago, 7, 8 years ago, I really don't know why I first got into double stars. I have absolutely no idea. But now I'm in it so deep, it's basically, there's a weight around my neck and it's just dragging me down. But no, it's been a fun ride, and there's a lot more ride to go. Anyway, this is not an apology, but rather a statement of fact. This is the first time I'm doing this presentation, so you guys are the guinea pigs as such. But anyway, the topic is, why double stars? Well, I've been asked that 1,000 times, and that might be the cheap and dirty answer, because they're there. This presentation hopefully will be the long answer. And I guarantee it will be long, but hopefully enough meat and stuff in it to make it exciting. My hope is to spark your curiosity in the area of astronomy that today still holds an important role in astrophysics, a full 200 plus years since the study of double stars began in earnest. Somewhere in the part of what I'm going to be doing through this presentation today is really just to give you an overview of literally the road I sort of took as I found myself in double stars. Somewhere in the latter part of 2009, I came across Sissy Haas's book, Double Stars for Small Telescopes. So I ordered it online, and a week or so later it arrived at my door. With great anticipation, I removed it from the packaging, admired its cover for a moment, and then opened it up. What? No pictures? So I'm not sure what I was expecting to find. I guess I was initially disappointed. Like most of you in the hobby, and I don't think I'm wrong on this one, we are all visual types. And a picture tells us so much more. And maybe it's because we don't want to do the work that reading requires. I want to leave you with a negative impression of it, so I'll come back to it, to Sissy's book a little bit later. As with the weather, so go observing fortunes of backyard astronomers. And being rather early in my astronomy hobby, winter excursions into the cold outdoors in search of dark skies was not a high on my priority list, so Sissy's book remained a minor curiosity that winter. Slide 5. Given my initial disappointments, I kept on looking online for images of double stars and related readings. In the early part of 2010, I came across another double star resource, the very new Cambridge Double Star Atlas by James Mullaney and Will Tyrion. And I think most of you know the charts that Will Tyrion does. They're absolutely gorgeous, and they're so easy to read. Again, no pictures, but at least I now have some star charts. Got copies actually of both the original and the newer version up front. We can look at those later on. These are great star charts, and anyone who recognizes the name Will Tyrion will know his star charts are some of the best available in that they are easy to read, providing the right amount of detail to navigate the night sky. As with Sissy's book, I will come back to this atlas again a little bit later on for some more detailed review. Okay, so now it's spring 2010. I've got my atlas in hand, and I head out on any clear evening to hunt double stars. I want to let you know in on a little secret about how naive I was at the outset. And I think this is an error that all newbies make in this astronomy hobby, especially when they don't have someone around to mentor them or offer them guidance and so on. So here's the process I started with. Select a star chart containing a portion of the sky readily accessible to me, and then head out into the backyard. Then I pick a labeled double star from the chart, star hop to its location, and this with total disregard for the data in the back of the atlas. If anybody knows this atlas, it has detailed data about the various doubles that are contained or noted in the map. So I basically just totally disregarded that information, just dived into the charts looking for double stars. They were quite easy to find. So that was what simply meant then is that when I started heading to these locations, and unfortunately the focus isn't that great in it, is it? But there are, anyways, many stars in that particular page, or systems in that page. So when I arrived at my destination, I had absolutely no idea what I was looking at, literally. So on occasion, I would find very obvious pairs. There are lots of pairs that are nice and bright, double, easily separated, so they're easy to see. But there are not many of those. And on most occasions, I would find a single star, but I was hard-pressed to find its companion. This went on for several evenings over a number of months until I came to the conclusion that there has to be a better way. I don't know if any of you have ever tried to scour the internet for pictures of double stars, but there really aren't any. So at this point, not being able to find anything, it was kind of frustrating. And so I'm not sure, again, at what point I finally decided, but I should note here that most of my excursions at that point were being done with a 3-inch, a fairly good 3-inch achromatic refractor. Nothing that you would call a light bucket, but certainly was certainly capable, a very capable grab and go scope. About this same time, I'm experimenting with eyepiece projection photography, which is simply using a telescope as a large telephoto lens and placing an eyepiece just before the camera to increase the magnification. So my first target was the sun, the moon.
You missed.
and this, you can't miss it, you know, it's not a hard one. So anyway, funny enough, this was just a by chance photograph, and if you note, here and here are what's called the lunar X and V. Now these two objects happen to be visible for about 8 to 12 hours every cycle. There's an 8 to 12 hour period that you can actually see these. I just happened to be out imaging that night and happened to catch it. So, and I didn't find out till probably 4 or 5 years later that they were actually, something like this was actually a recorded observational item that people would actually take time to try to capture and try to observe. So it's funny how when you get out taking photographs, what will turn up in a photograph, and you really don't expect it. So next, here's a larger version. Again, these are early photographs, not terribly well focused. You can see there's a little a violet fringing going on in here, but again, there's the X and there's the V. Very, very simple and plain. So after the moon, I started heading for other stellar type objects, and again, unfortunately, the photograph doesn't resolve itself very well here. But this is NGC 2169, the 37 cluster in Orion, and it's actually, this is the a reverse flipped image view. Its actual orientation is properly in the 37. There's the 3, and there's the 7. So this was an early eyepiece projection. If you might note these little footballs all around the outside. These early photographs that were actually taken with celestron plausibles. Center of the image was fairly crisp, but the outside edge, you could just see everything just getting prismatic effect on all the outlying stars. So at this point, you know, the light bulb goes on to say, okay, I'm going to start a project. So back in 2010, in fact, Bob knows about this too, I had some early discussion regarding this. I started on a project to image 5,000 double stars. And so the idea was to image stars that were accessible to 3 and 5 inch sort of refractors, things that, you know, typical backyard astronomers would have. I consider it sort of something in an 8-inch Dob, something of a backyard scope as well. Long focal length refractors and SCTs are the preferred scopes of choice of seasoned double star observers. But as James Sophia will know, an 18-inch ultra-compact obsession makes a real fine double star scope. A little overkill, but it does a wonderful job, especially on the really dim stuff. So anyway, so my goal was to complete the project in 10 years, which meant imaging and processing about 500 double stars per year, or roughly 10 per week. As fortunes would have it, life has a way of getting in the way. So getting in my 8th year now, my count is about 2,500. So I'm about halfway through my project. So with a few other earlier items, I will be revisiting that my project later on, some of these stars. In reality, though, because there are when you pick out a list of double stars, you get them on you create a list of it, and you get your coordinates and so on. The reality is, many of these star fields that you have within your field of view of your camera and imaging setup, you end up actually getting 2, 3, sometimes 4 and 5 separate systems, catalog systems in the same image. So I'm probably closer to 3,000 double star systems that I've imaged to date. So, first question that I'll throw out to the crowd: what constitutes a double star? Any takers? There are a few people who have a little bit of double star theory. Sure.
2 stars that are gravitationally bound, most likely born at the same time out of the same body of gas and whatnot.
Generally heading in the right direction. The reality, well, after you've done the reading and sort of been around it a little bit, double stars initially started as just that, 2 double stars. Back when the first double stars were being talked about and discussed, nobody knew about gravity. Okay, back and I'll be a little more detailed. I don't want to get too far ahead of myself, but you think back. I mean, astronomers before, back in the ages before Christ, they were seeing naked eye stars that were close to each other, and even in those times, there were a few of them were observers were actually identifying or talking about them as being double stars. Nobody had any notion as to what the gravity connection might be. So at this point, let's just safe to say that a double star means theoretically 2 at this point. Whether they're gravitationally bound, that's another item. So
Yeah,
now,
but Chris, they don't look like, they're not, but originally they look like 1 star, right? And then you apply magnification and you see that it's really 2 stars.
For us, yes, maybe.
Yeah.
But if you think of the early observers, they didn't have telescopes.
Right.
Okay, so there are lots of stars or pairs of stars that are fairly close that look very much like a double star and would have the same sort of look if you were to take something of a smaller, more compact nature and look at it through a telescope. So, but in any case, so over the past 8 years, I have learned, and you might not be expecting this one, that a double star is only a double star if it appears in the Double Star Bible, the Washington Double Star Atlas. There are,
that's true.
and I'll show you photographs of many photographs I've taken, all kinds of things what you would expect to be double stars, but they haven't been cataloged, so they're not a double star. Okay, so if the activity in double star, the first double star collectors, if you want to call that, and I'll again be more detailed, they were basically, they observed these things, so they started cataloging them. You know, and they were close, and more often than not, they were probably just in, serendipitous inline sight stars. Okay, it wasn't until much later on that one understood, one learned and understood what the impact of gravity and how you could get, what are called binary pairs, and they would be in fact proper double stars in the sense that they were gravitationally bound. So anyway, I just want you to keep in that bit of mind. But like I say, it's only a double star if it appears in the Washington Double Star catalog. So anyway, the WDS, which we refer to it as the Washington Double Star catalog, the WDS, is maintained by the United States Naval Observatory, or the USNO, as it's affectionately referred to as. One of the things that you will learn early on in this endeavor is that the name double star is a bit misleading. Why? Because these are double stars. This is our 37 cluster, 169. This is a system. This is another system. This actually belongs to this system. And I'll show you this a little later on. So these are what we call our Struve 848 and Struve 844. So there are two double stars, and there's certainly more than two in either one of them. So again, the double star and people in the study and research of this area do refer to multiple stars, but double star is basically meant and used to mean anything that's two or more stars that have been sort of cataloged and later on proved to be either gravitationally bound or not. So now, you may not be able, you can't see it in this one. There is a little double down here, and it's called CLU1. It's just a very faint pair, and unfortunately, the resolution here at this sizing of the scaling of the drawing or the picture doesn't show it, but you can certainly see it on a computer screen, and I can maybe show you that later on. So anyway,
Chris, is angular separation part of the definition?
no, not really. No, really, the cataloging purpose of talking about angular separation and the position angle are basically just data that are attached to the double star. They aren't part of why a double star is a double star. They're used to basically record its activity, and that's really what the position angle and the separation are doing. They're actually recording over time how the movement of these stars is amongst each other, but they in itself do not constitute aren't a reason for calling something a double star. Okay, so every double star, every multiple star has got various records of calculations and so on, and we'll get into that in more detail. I'm trying to avoid a lot of detail early on here because I wasn't even in that headspace when I started this. I started this out as a photography project, literally, and as you start meeting people, you start going to double star conferences and stuff like this, suddenly you sort of get dragged off into a direction you didn't really plan on going, and as a result of that, my photography portion of the project has really not suffered, but again, it's the whole notion of learning everything, what there is to know about this area of astronomy has just, it's just ballooned so fast that it's just consumed so much time. My photography portion of it just hasn't been able to keep up to my original plan. So it may be a 16-year plan and not a 10-year plan. So anyway, where are at slide? Oh, something I should mention right away too. All these background photographs are my own photographs, and these are older photographs, some of the earlier ones. You'll note too, there's a slide number up here, and you'll see this on every picture. There is the actual name of the system, and as you get into the further on slides, buried in the text are these double stars. They're fairly obvious, but sometimes you have to look. So if there's anything on any of these slides that you want to talk about later on, or just bring up a question later, just remember the number up here. Jim, can we shrink that down just a wee bit, just so that number doesn't get lost up there?
Yeah, you have the remote is up there in front of you.
Okay, so which button on the remote do I hit?
Towards the top of the remote, there's a zoom.
Not the D.
Next to it.
The D zoom?
Not the D zoom, there's another zoom.
Oh, at the top.
Yeah.
Plus minus, okay. So I'll just get that number a little further away from the corner. Now, will this go on? Yeah, good, it's gone. Okay, so just keep that in mind. So and the format of every slide is the same. It's one of typically one of my pictures, and then I've got the label down here of the actual catalog name of the system, and then a slide number up here. So if you want to refer to it later on, if there's something that shows up on a slide that you want to talk about, please do. Okay, so we're at slide 11. Okay, let's go on to. Okay, this is, and again, I don't want to dwell on this a whole lot, but because we can talk more about it. This is a website called Stelladopy, and what it basically takes all the Washington double star information and puts it into a much more accessible user format. The database on the Washington double star site is purely just a very basic spreadsheet. Very, unless you really know it real well, a little awkward to read and a little awkward to find everything. Everything is laid out from right ascension, so you start at 0 and then it just travels to hour 23 hours and 99 minutes before it hits 0 again. So everything is listed in that. It's not listed by a constellation and so on. So Stelladopy does effectively, it doesn't get itself into a spreadsheet sort of format. What it does is that you basically, you can log on up here, you insert a catalog double star that you want to find. You put it in here, you hit the enter button, boom, all this information up. You saw that earlier photograph. Oops, sorry, gone the wrong way. Let's go back up. Okay, so we're looking at 848, Struve 848. That's what I pulled up here. There are actually 20 visible stars in this system. And just to let you know, if you look right here, it talks about the nature of this double is uncertain. The reality is most of these stars are not gravitationally bound, but for some reason they've been included in the cataloging of it. And a lot of it is just to get additional reference positions from other stars within the system. Again, I don't want to get too complex here, but you can see, for instance, here's Struve 848, and it lists AB, AC, AD, AE, and ABF. At ABF, then you're into another label here, but these are all part of that same system. So you've got an ABH classification here, you've got a JNN, you've got an SLE, and more JNN. But anyway, there's 20 stars that create all these sort of combinations of 2 stars. And I'll get into more detail later on. The wonderful thing about this too is that once you call up one star, especially with me and my work when I've got images that are probably taking about 3 arc minutes of area of sky that's in each photograph, I can just go look over here and start to say, oh, okay, geez, look, I got a bunch of stuff, nearby doubles. So when I started, when I found this site, and it's a relatively new site, so when I would take my photograph, look at the information, then compare it to this, and then I started to realize, gee, I got 3 or 4 additional systems in that one image, and I didn't even know they were there. The one thing I've been doing with my imaging is I'm trying to take a large field so that I can give somebody later on down the road who's looking at these things a frame of reference. Most of the stuff you'll see sketches that are being done, you can see on the internet by, I'm trying to think of his name, that does all the sketching. Robert, do you know who that guy is?
Handy?
Who's that?
What's his name?
Perez.
Oh, that's what I said.
Perez does a lot of double stars. But anyway, they're just small little things like this, and that's all you see. So if somebody's looking at a photograph to try to find out if they're in the right place, you got to give them a little bit more area. So my photographs have been limited to working with double stars that have a 5 arc-second separation. Beyond that, if they're very, very dim, I can get a little tighter pair, but 5 arc seconds is about the limit of my imaging setup. So that's somewhat limited. And so just to give you a quick brief thing on Stelladopy here. So anyway, this is the WDS designation right here. These are the coordinates. This is the RA. There's the deck. It talks here about date it was first observed, and it looks like 1826. Date of the last is 2016, and it's been observed 64 times. And it talks about a PA, which is the position angle of first. And of course, right now, we're talking about AB only, so it's just this top row here that we're looking at. You can, down this row, you can hit any one of these, and you can get the more detailed information. It says, basically what that is saying is show me. So hit that, and it'll show you the detailed information on that. So it'll take this information, bring it up into here, and you'll get more data on the first and last, the PAs and the separation and so on. I don't want to get into that now. That's that's a conversation point at this point. So I've been looking at that screen, so it's like it's too bright. I can't even read my. Okay, that's better. Okay, so we'll head on to this slide. So basically here's our 37 cluster again. Now here's the thing, you can go to this website, Aladdin, which is part of the University of Strasbourg. They have an incredible website of information, useful for double stars, all kinds of other work. And hopefully, if there's enough interest, at a later date, I can do almost like a workshop setting, have access to the internet and do some of this sort of research in front of you, just to show you how to get through some of these sites. But the problem with these images from Aladdin, which are these the digital sky surveys, I mean, we're looking at stars at magnitude 18, 19, and 20. And the reality is, when you're looking through a backyard telescope, the only thing you're going to see is that. Okay, and that's the nice thing, or the good thing about these photographs I'm taking, is that the imagery that I'm getting, and I've been fairly good to be able to control that, is I'm sort of getting to mag 11, 11 and a half, sometimes 12, sometimes 12, and a lot of that depends on how good the night of my imaging is, and so on. So, but in reality, then it's giving you a photograph of what you're really seeing. This you won't see through a telescope. Typical backyard. There's just way too much information. So it really pulls away from the actual double that you're looking at. And it's when you start looking at these doubles and you actually go in there and so many of them, you'll see this in later photographs, is that all you're seeing are two stars, and you sit there and you say, how can these two things not be tied together? Because they're the only thing in your view, and you're looking at it. It's really a strange sensation, because there they are, two stars. How can they not be tied together? In many cases they are, and other cases they're not. So what am I going to offer here? Well, I'm going to pull back one or two layers of a very large onion I call double star astronomy. To do otherwise would be impossible in a single lecture. And my disclaimer is I'm no expert of the subject, would suggest that I know enough to be slightly dangerous, and I'm quite prepared to be extracting my foot from my mouth every now and then as I go through this. So, again, this is Grapheus, or 8 Scorpio. There it is right here. Pretty much no other stars in the field. And that's a fairly wide image when you think about it. So when you come on an image or on in your telescope, and that's all you're seeing, you sort of say, it's a no-brainer. They've got to be related, but like I say, in many cases they aren't.
So Chris, do you use the same power eyepiece?
Well,
because
good question.
Yeah,
for the and again, everything I've done from the beginning is all a learning process. I mean, the pictures I started taking at the very outset don't resemble anything what the pictures I'm taking now. My early pictures were taken, like I say, were taken with celestial plausibles. Then I moved to Hyperions, and they were giving me a little less of that footballing on the outer edge. Finally, I found a Celestron Barlow, 2.5 Barlow, that just about eliminates all that footballing in the image, and I'm just getting just a touch of it on the outside. So what that's meant is when I was going in to process these double star images early on, if you remember that earlier photograph, that real chromatic gradation through the football from blue to red and so on, but most of that was being lost as I'm sitting there trying to clean up, tailor these things into round stars. And of course, part of the ballooning process of them getting spread out like that, you're not really sure how big that star needs to be trimmed down to make it realistic. So obviously, just through the process, everything has changed. And right now, the intent was to make all 5,000 photographs at literally the same field of view. So when you start looking at them, you can just, it's incredible the amount of variety, variation, and just in that same size of photograph. If all you're getting is this narrow little field around a double star, you really don't get any appreciation for what it really is until you get something. And I think that goes with a lot of what we observe in astronomy, is that if there's no reference around it, then it's, many things look great in a very wide field view, and many things look terrible in a wide field view, and you have to go in and focus. But I think for the most part, especially doing things like messy marathons and stuff like that, it's always nice to see something of a reference around to which you can tie the thing that you're looking at together with. And that's why I've taken my photographs at that wide a field, and why that's limited me to that 5 arc second. So generally, to answer Jim's question, I've tried to maintain that same field of view. It's gotten a little little narrower since I went to the 2.5 Barlow, but it's almost imperceptible in terms of when you're comparing one photograph that was taken with it was a 13 millimeter Hyperion that I was using on an f9 4-inch Skywatcher. In fact, I'm using same telescope, everything, nothing changes. So every picture I take of a double star is taken with exactly the same equipment, so that I'm trying to get that comparative nature of these photographs all the same, so that you get the same.
And you're still doing eyepiece projection?
Well, I'm not, it's not, I put a Barlow in instead.
Okay.
I've eliminated the eyepiece and it's basically the same thing, effectively. You're using a lens to create magnification, but I found that the 2.5 Barlow gave me exactly, just about the same image size as the 13 millimeter Hyperion, so.
Okay.
Okay, so anyway, that's my disclaimer. I don't know a hell of a lot, but I know a little bit. Okay, so the goal here then is to hopefully excite many of you, and I guess there's a number of here that have actually done some double star imaging. It'll be interesting to talk to them later on. So anyway, here we've got HJ607. That's actually for John Herschel, 607, 608, and HJ2943. So there's one pair, and there's another pair, and right over here is a very, very dim little pair right here. So there are 3 stars in the same field, just happened to be there, and I would have been aiming for one or the other, and just so and that's when you start doing the research. You realize, and the thing is, I didn't know about that Stelladopy site until probably image 900. So everything behind has got to be brought back up. So every time I change tweak one little thing, then of course you're feeling compelled to go back and sort of bring everything back up to the same new improved version. So anyway, I'm going to start the sort of the more formal part of the discussion, and it's really not about so much the double stars. Let me see if I can kill this now. Get my eyes reaccustomed. Whew, that's amazing. That's why you don't use white light when you're doing astronomy, I guess. I may have to use it. This one. Get rigid enough here. Okay, so we are at slide 16. So I'm going to get down here. Okay, so what you've got in front of you are 9 key figures. There are many other characters in this story, but these represent the most recognizable players in the road to modern astronomy. It might be useful to note here that the word astronomy had its first recorded usage about 1200 AD. So they weren't called astronomers way back then. In fact, the term natural philosopher was the more common term, shall we say, sort of after zero. In other words, in the AD, the BC period, they probably didn't use the word philosopher. At least that would be my speculation. But anyway, so we've got basically what we call the ancients. We've got the Renaissance, and we've got the Age of Enlightenment. It's curious to note the ancients are all Greek. The Renaissance and the Age of Enlightenment, all European. And I speculate a lot of this had to do with the fact of the impact and the, well, I wouldn't say the power, but the fact that the Catholic Church was a very strong influence in all of this, simply because it kept a lot of information in its control. As you'll find out as we talk through or go through later people involved here, they were mainly all very religious people. In fact, most of them were either deacons or priests or monks, Jesuits, and so on, believe it or not. And so and a lot of that, I think, was because through the religious power of having access to just information, all these things, they tended to people of any kind of knowledge tend to stay together and communicate with each other, and I think that's basically what you're seeing happening in here. Okay, so we'll go on to here. So first we have Aristotle, 384 to 322 BC. Greek philosopher who proved the earth was spherical and believed earth was the center of the universe. Now this surprised me a little bit when I found this out. I didn't realize the notion of a round earth actually went that far back. I mean, if I recall through my grade 5 and grade 6 history and stuff like that, there was always discussions of sailors, sailing off the end of the earth, still in the time much more recent than this time. So it really surprised me to see this. Then we have Aristarchus, 310 to 230 BC, Greek philosopher who was the first person to suggest that the sun was the center of the universe. A full 1750 years before Copernicus. This theory was considered far too radical. So, but again, you've got people at this time, really, they do have it right. And you sort of wonder, when you look at these ancients and you sort of say, God, if they had the tools and the knowledge and the information base that we had today, what kind of people they would have been. Next we have Hipparchus, again, 190 to 120 BC. Greek mathematician who is considered the greatest of all ancient astronomers, compiled the first known star catalog. He devised what may be the first known scale to divine the brightness of stars, and he measured the Earth to Moon distance to be 29.5 Earth diameters. Phenomenal when you think the actual measurement is 30. So if you can just understand how it's for me, just knowing and understanding these guys, it really is boggles the mind that they had the ability to do this in an era when people were still thinking things might be flat and that we're still trying to sort out whether the sun was the Earth was revolving around the sun. What's even more incredible is his greatest discovery was that of the wobble of the Earth. This is back in 120 BC. This is phenomenal.
What did he attribute it to?
I have no idea. I didn't.
Bad accident.
Well, obviously, it's just observation, understanding, and he must have been seeing things happening in such a way. But again, I didn't want to get too much into that. So this is Struve 3003. There it is, sitting up in here. So you'll find, this is what I mean. You'll find them buried in the text. I sort of had to move my text around the stars. And of course we have Ptolemy, mathematician and astronomer of Greek descent living in Egypt. Using extensive observations of Hipparchus, developed a model that predicted the movement of the sun, moon, planets, and stars on an Earth-centered universe. This model was one of the longest upheld scientific theories of history and the cornerstone of astronomy for 1,500 years. Hard to believe. Well, I guess it's kind of important to remember when we mention the word universe, the universe obviously is quite small at this point, and it basically involves the sun, the moon, the earth, and the known planets at the time, and obviously the stars that were readily available. So again, we have to, when one sees universe, it's the much smaller universe than what we know today. So with Ptolemy, we get the first references in written form of a curiosity for double stars. This is HJ 3780, and I believe there's 4, possibly 5 stars in that system.
So if he was detecting what, just separation?
Well, well, this is just it. First of all, his was all naked eye, and this is what I was talking earlier about naked eye, close doubles. So the 3 that he has literally, what you'll find in his literature is mu1, mu2, and Scorpius, which is down here. Nu1 and Nu2 in Sagittarius, which is this pair right here. And then Xi and Nu in Orion, which is up here. Here's Betelgeuse, Rigel. So these two stars up here. Remember the 37, the NGC 2169? It sits about right there. So something to look at next time you're there. But anyway, so these are the naked eye stars that were referenced in Ptolemy's discussion.
Yeah, but
Now,
how did you know those were double stars and not
he didn't.
just-
Again,
Oh,
remember, double stars. Just
Right.
literally, all it meant to
Two
most
stars together.
was two stars in close proximity, and nothing more. Because again, nobody knew gravity. What the hell's gravity? Why would they think they would revolve? They had no notion of it. So when these first early stars was purely just noting, okay, these stars happen to be close to each other.
Yeah.
Now, this is a name I don't. Some of you may know. Bruce McAvoy has an absolutely incredible website dedicated to astronomy. He's got a large portion of it which is dedicated to double stars. In fact, he is the sort of the co-author of the second version of the Cambridge Double Star Atlas. Bruce went in and did a myriad of corrections and so on. But we'll talk a little bit about Bruce. But on his website, he talks about and references saying that this pair of naked eye stars is sort of has about a, if you're looking through a telescope and eyepiece that gave you about 100 times magnification, this would be about a 4-second arc-second separation. So, and now he's saying that this is actually 6 arc minutes. Well, it was funny last night when I was reading through my notes and going through this. I said, "Shit, that isn't 6 arc seconds. No bloody way. It's much smaller." Anyway, as it turns out, there's some error in there, and I need to consult or talk to Bruce about it and get maybe there's something, because definitely I didn't get it wrong from his website. He definitely does have 6 arc minutes there, but this is more like 1 arc minute. But in any case, the point, what Bruce is trying to do here was trying to give a little bit of a reference to what a naked eye observation might be to an eyepiece at 100 point. Now, this 4 arc seconds happens to be actually just about the limits of my imaging setup so far. So here's another one, Omega-1 and Omega-2 Scorpii, but Ptolemy, for whatever reason, negated to talk about them. So, but anyway, there's another group right there. That happens to be Jupiter. Okay, in this case, Bruce suggests that this Nu1 and Nu2 in Sagittarius have about a 9.5 arc second, or a little greater than twice what we saw in that pair in Scorpio. So we got Ptolemy's cluster M7 over here, M6 there, M22, M28, M8. These are just photographs that I took over the years, wide field look. And this one, he suggested, would be 40 arc seconds, which is quite wide, and it is quite wide. So, next, Nicholas Copernicus, mathematician, astronomer, Renaissance thinker of Polish-German heritage, who turned the world upside down with a sun-centered model of the universe in his book. I'm not sure that I want to attempt the Latin, but it's on the revolutions of the celestial spheres. Polyglot and polymath, these are 2 words. I don't know if anybody's familiar with these words. A polymath is a person whose expertise expands a significant number of different subject areas, such as a person is, and in his case, well, the full list isn't here, but what it basically means is polyglots tend to take all this expertise from all these differing subject areas that they have significant strength in, and they pull from these things to actually solve a problem in one isolated case. They'll pull information from different areas of information expertise to pull it together. A polymath is simply somebody who has good control of several languages, can read and write and communicate in several languages. So he was a universal man. His expertise spanned many disciplines, including canon law, astronomy, medicine, the classics, translation, politics, economics, and mathematics. And again, the information here on canon law, you'll find a lot of these scientists in that period and the double star observers who just happen to be part of that same group have all connections to religious. They're either involved directly as priests or canon are involved in canon law or so on. So anyway, Nicholas Copernicus was not 4. There's a big wide double right here. Now, and a couple of things I'll just quickly go. I have a couple of notes on Copernicus. It's important to note that for Copernicus, his astronomy activities were restricted to his spare time. His preoccupation with his role as a canon in the church, which is basically, if I understand correctly, is basically dealing with the laws of the faith. And that's sort of where his activity was. So his full-time job was that, and this was done in his spare time. And again, what you'll find through most of this, through most of my research, is almost all of these early astronomer types, and again, you have to use the word astronomer kind of loosely, because first of all, most of them were not paid. They were really not taught in astronomy because there wasn't really a lot of astronomy education available. Most of these guys were learning astronomy on their own simply because they had a special interest. If anything, they had a mathematical background which led them to the astronomy. In the end, his theory of a sun-centered universe did not receive wide support. Most thought he was a fool. Surprisingly, in my research, I did not find very much to indicate that his views on the sun-centered universe led to much repercussion, as was experienced by Galileo. And I suspect it had the fact that he was really well tied into the church. So in spite of him basically trying to say the same things that Galileo was saying about a sun-centered universe, because really it was our solar system we were dealing with, he never received any repercussions as a result.
That's because he published his stuff. Stuff was published after he died.
Well, but still, if you're studying it and talking about it and teaching it, you wouldn't be. You'd still be. Tycho Brahe, interesting character. This one. There's a story attached to that one. Anyway, some interesting quotes from one of the biographies I read. Well, maybe we'll just go through some of this. Danish astronomer who made the most accurate celestial observation of his time. In 1575, the King of Denmark enticed the now famous Brahe to stay in Denmark by offering him his own island and financial support for his research in astronomy. Astronomers were extremely popular people. Something else to note, that the terms astronomy and astrologer were almost synonymous in that period of time. Now, and I'll get a little bit more on that later on. So Brahe was not a supporter of the Copernican sun-centered universe, but rather postulated that the sun and the moon orbited the Earth while the 5 planets orbited the sun. His contributions to astronomy were enormous. He designed and built instruments that revolutionized astronomical instrumentation. And there's our oaws21 hiding right in there. So anyway, here's some of the interesting notes I came across. And this was basically a sort of one of several biographies that was written about him. And while most people may think of scientists as stodgy academic types, Brahe's flamboyant lifestyle and ignominious death would have made some of today's wild celebrities look like choir boys. In 1566, a 20-year-old Brahe fought a fellow student in a duel over who was the better mathematician. As a result, he lost a large chunk of his nose and for the rest of his life wore a metal prosthetic to cover the disfigurement. I think they were both drunk at the time. Apparently, Tycho liked his drink. He was quite the partier. So Bray goes on to say a little bit more about his death and says, Bray died in 1601 at the age of 54. While attending a banquet, societal customs did not allow him to excuse himself before his host. Bray had drunk obsessively but refused to leave to use the bathroom. So it is thought that this caused his bladder to burst and led to his subsequent death. kind of blows your mind.
Did you say
So-
he got in a duel in 1556?
He was 20 years old,
10 years old?
1566.
Oh, 66.
Yeah, 66. 20 years old. So in 1901, his grave was exhumed to mark the 300th anniversary of his death. So scientists at the time claimed they found mercury in his remains, fueling rumors that the great astronomer was poisoned. Some even accused a jealous Johannes Kepler of the crime. Bray's body was exhumed again in 2010. Tests on his bones and beard hairs showed that mercury concentrations in his body were not enough to have killed him. There were several other metals found in his system that may have contributed to poor health through a slow poisoning of his system. These other metals can be attributed to the nose prosthesis, which appears to have been a combination of copper and zinc, because they found a fair amount of green staining around his nose. Kind of hard to believe they'd be able to find that after 400 years. But anyway, they did. So there's some speculation that he also dabbled in alchemy. Researchers found large amounts of gold in his system as well. So I guess they weren't into drugs. They were just doing hard metals, I guess. So anyway, just getting back to this notion, and you can see the King of Denmark offering him this land and so on. Well, anyway, and it talks about astronomers and astrologers being much sought after, and two reasons for that. Certainly wasn't for their astronomy. Number one, primarily it was their ability to develop and read star charts, which of course are key for navigation on the sea and so on. So if you have a strong navy and you're out conquering the world, you want a good astronomer around that knows how to generate maps for your navy. The second thing is that time most leaders. I suppose we have a few superstitious leaders here, but the reality is these so-called astronomer types who were often asked to read the stars. So a lot of these kings and rulers of the time were depending on guys like Tycho Brahe and other astronomers to give them good astrological reports as to what was going to happen in the next battle or whatever. So it gives you a bit of an insight as to why so much importance was generated around Tycho Brahe, and the King of Denmark wanted to keep him close by. So, Galileo. Italian polymath, central figure in the transition from natural philosophy to modern science. And again, philosophy, and it's used quite frequently even in further on in history. But really, when you see philosophy or philosopher, it really means scientists. But in reality, Galileo sort of dragged everybody from that sort of notion into modern science and in the transformation of the scientific renaissance into a scientific revolution. Now, Galileo supported the Copernican heliocentric model of the universe, but unlike Copernicus, was considered a heretic and spent his later years under house arrest. Now, Rob seemed to think that more so because Galileo was a little more outspoken about it. I assume Copernicus should have been or would have been a little bit. Would have talked about it, I'm sure, but for whatever
Copernicus chickened out, Chris.
Yeah,
right?
no, I think it was better connected. So anyway, Galileo builds his first telescope in 1609, based on the design of a Dutch optician. Upon turning his new telescope to the heavens later that year, his new discoveries included the 4 brightest moons of Jupiter, the phases of Venus, and began the analysis of sunspots. He also discovered something unusual about Saturn, but his telescope lacked the power to discern the true nature of the rings. So there's a Struve 2562 sitting in there. So Galileo was known for his work as an astronomer, physicist, engineer, philosopher, and mathematician. He has also been often referred to as the father of observational astronomy, father of modern physics, the father of scientific method, and the father of science. And might be the father of all of us if you've given them the chance, I guess. So early on, just thinking of these first telescopes, these were really intended for naval use and armies and so on. And for whatever reason, I guess Galileo was the first one to sort of say, hey, geez, this kind of makes sense. I might as well look up into a dark sky. And it's funny how these things sort of just happen sort of with absolutely no explanation and so on. Now, Johannes Kepler, the guy who theoretically poisoned Tycho Brahe, but no, he didn't. So Kepler was Tycho Brahe's assistant and student. Building on the detailed, accurate astronomical records, he developed his 3 laws of planetary motion. He believed in the Copernican heliocentric universe, but could not reconcile Brahe's observations to fit a circular orbit. So with some slight adjustments and using an elliptical orbit, he found that Brahe's observations could be better explained, and this led to his first law of planetary motion. He invented an improved version of the refracting telescope, which is referred to as the Keplerian telescope. Kepler was a much sought-after astrologer for those kinds of, for the obvious reasons. At this time, there was no clear distinction between astronomy and astrology. In spite of a long working relationship between Kepler and Tycho Brahe, Brahe was very protective of his records, thinking that Kepler would cheat him out of any financial gains. It's amazing the interplay with these learned men of the time, very, very protective of their information.
Brahe didn't want Kepler to find out the sun-centered universe. So he was refusing to give the records to him so that Kepler couldn't prove the sun-centered model.
Yeah. Well, anyway, he finally did. He finally did get a hold of all of his data. So just a little bit of data on Kepler. He was introduced to astronomy at an early age and developed a love for it that wouldn't span the entire life. At age 6, he observed the great comet of 1577, writing that he was taken by his mother to a high place to look at it. And in 1580, at age 9, he observed another astronomical event, a lunar eclipse, recording that he remembered being called outdoors to see it and that the moon appeared quite red. However, childhood smallpox left him with weak vision and crippled hands, which severely limited his observational aspects of astronomy. So ultimately, he really became Tycho Brahe's computer, if you want to call it that, figuring out and doing all the calculations and so on. Now, Kepler set out the theoretical basis of double convex converging lenses and double concave diverging lenses and how they are combined to produce a Galilean telescope, as well as the concepts of real versus virtual images, upright versus inverted images, and the effects of focal length on magnification and reduction. So we go on, Kepler again. He basically, from Tycho Brahe's data measurements, Kepler developed the Rudolphine tables, which provide the data to calculate planetary positions for any past or future date. So Kepler was a mathematician of the best kind. He was born premature and was a sickly child throughout his youth, but a sharp mathematical mind impressed all those who came in contact with him. And of course, we talked about the smallpox. So this bottom magenta quote here is something that I found. It says, though frail of body, but robust in mind and spirit, Kepler was scrupulously honest to the data. So in other words, he did everything he could to make it, to use and make the information correct. Here again, we've got a couple of systems. There's one here and another. These are running this way, bright, dim, bright, dim. These are running vertical. These are BU, or Burnham 324 and South 528. So the University of Padua, on the recommendation of departing Galileo, sought Kepler to fill the mathematics professorship. Kepler's law of planetary motions were not immediately accepted. I wasn't aware of that either. And several major figures, even Galileo and René Descartes, completely ignored Kepler's Astronomia Nova, or the new astronomy. Many astronomers, including Kepler's teacher, Michael Maitland, objected to Kepler's introduction of physics into astronomy as an alternative theory to God, to a God-controlled universe. This in spite of Kepler's deep religious convictions. So here we have a very religious man introducing scientific theory into astronomy in direct conflict with his own religious beliefs. So you can start seeing the conflict of religion and science really starting to take effect. Let me jump back here quickly. There's one other little comment here. As one does more detailed research with key characters in the new astronomy, it becomes quite clear the great distrust that they had for each other in spite of cordial discourse that they had. And this is probably will be the bigger surprise to you. Certainly for me, Sir Isaac Newton was quite a surprise, not from the scientific side, but certainly from his personal side. Anyway, here's some of his highlights. Discovers that white light comprises all colors of the spectrum. Postulates the light is made of particles. In 1672, Newton publishes Optiques, which was a treatise of reflections, refractions, inflections, and colors of light. In 1687, after much encouragement from Edmund Halley, Newton publishes his most important work, the Philosophia Naturalis Principia Mathematica, or Mathematical Principles of Natural Philosophy. Again, this whole notion of natural philosophy, really, it's just mathematical principles of science, and it was simply referred to as the Principia. In it, Newton lays out his three laws of motion to become the foundation for his theory of universal gravitation. That's the key word, universal gravitation and double stars. That's really the connection that we want to make here. Along with Gottfried Leibniz, Newton is considered the co-creator of the mathematical principles of calculus. In 1668, he builds his first reflecting telescope, which provides better images than earlier refractors, and it's called the Newtonian telescope. He eradicated any doubts that the heliocentric model was correct. So with Newton, everybody finally had to say, okay, sun is the center of our little universe, or our solar system. Anyway, Sir Isaac Newton is actually a fairly interesting character. A lot of interesting biographical information. And so I'll just read through some of these notes. I guess it is only human nature that we want to protect our hard-earned knowledge from others. Sir Isaac Newton may exemplify this fear more than any other great thinker. He was very reclusive, very rarely published his work, unless other trusted and respected friends encouraged him to do so. I'm not sure that astronomer is really a good adjective for him, or something to describe what he was, because there's almost nothing in the literature that talks about him doing observational astronomy. So I suspect most of his information and with regards to the positions of things was all based on other astronomers, probably John Flamsteed for one, and the previous astronomers, Tycho Brahe even as well. So I really don't see him as an astronomer. Sure, he built a telescope, but there really is surprisingly little in the literature that talks about his efforts, exploits in astronomy. So here are some reflections that that I deduced from some of the biographies that I came across. The records show that Newton was an often difficult personality, and when placed in positions of power, was tyrannical in his relationship with his peers, often claiming authorship of the work of others. Throughout his life, he had run-ins with several luminaries of his time, most notably Gottfried Leibniz. He's the guy who the world has finally decided to say that both of them created calculus virtually at the same time. And again, a lot of this problem is that back in those days, they didn't have the ability to communicate with each other rapidly. Everything, I mean, you might get a letter 6 months later, you might send a letter and 6 months later you get a reply. So things happened slowly, and you can see quite easily something like that happens. You got two bright mathematicians working in the same area and having maybe had a conversation with each other and both coming up with the same notions at the same time. So eventually history has finally said that both of these people are responsible for it. But in Newton's lifetime, no, he was the only one that had discovered calculus, and he basically took that to his grave. So Newton suffered occasional emotional breakdowns during his life and was known for his temper. Early conflicts with other scientific figures of the time seemed to make him reluctant to publish or share his discoveries. His work on gravity was released only after the astronomer Edwin Halley visited him with a question about the motion of planets, and was confounding astronomers, and found to his shock that Newton had worked out the answer 4 years earlier and simply kept it to himself. A little hard to imagine. So given the rage that Newton had shown throughout his life when criticized, it is not surprising that he flew into an irrational temper directed against Leibniz. Perhaps all that is worth relating here is how Newton used his position as president of the Royal Society, and in that capacity he appointed an impartial committee, impartial, emphasis on the impartial committee, to decide whether he or Leibniz was the inventor of calculus. He wrote the official report of the committee, although of course his name did not appear as the author, which was published by the Royal Society. And he then wrote a review, again anonymously, which appeared in the Philosophical Transactions of the Royal Society. Now there's something I got introduced to by a double star friend from Washington State. And this is the Philosophical Transactions of the Royal Society, which is basically I guess the periodicals of the English scientific elite, if you want to call it that. Incredible reading, very interesting reading, and if you got nothing to do on a night and you get on the internet, it's some really interesting reading at any time. On all kinds of subjects. In fact, many of the things actually walk you through experiments and how the experiments were done and so on and so forth. So anyway, I won't say a lot about it, but the fact is that it's extremely interesting reading. So I go on. Newton's assistant, Whiston, had seen his rage in first hand. He wrote, "Newton was of the most fearful, cautious, and suspicious temper that I have ever known." So as Astronomer Royal, John Flamsteed spent some 40 years observing and making meticulous records for his star catalog, which would eventually triple the number of entries in Tycho Brahe's Sky Atlas. Unwilling to risk his reputation by releasing unverified data, he kept the incomplete records under seal in Greenwich. In 1712, Isaac Newton, then president of the Royal Society, and Edmund Halley somehow managed to get a copy of these Flamstein's data, basically broke in and took the data and printed 400 of the catalogs. So Flamsteed managed to gather up 300 of the 400 printings, and he burned them. So, and in Flamstein's own words to his assistant Abram Sharp, he wrote, "If Sir Isaac Newton would be sensible of it, I have done both him and Dr. Halley great kindness." So I guess just I guess he was concerned, he just didn't want poor data getting out there. So he just decided he had to burn it all up and get rid of it until he could publish his own. And I'm not sure it was published, his information, his catalogs were actually published after his death by his wife, I believe. So one paper that I came across speculates that much of this aspect of Newton's character has been downplayed by history so as not to tarnish the memory of the great thinker. It is interesting to note that all his work related to light, gravity, and calculus all occurred for the most part in the first half of his life. And in 1696 he was appointed to the role of warden and then master of the Royal Mint. There he spent the last 30 years of his life. This was supposed to be an honorary position, but as he needed a distraction from the mental strain of his scientific endeavors, he thrust himself into the position and was instrumental in moving England from the silver standard to a gold standard. not really double star related, but I think it's interesting stuff because it gives you a sense of these characters, and this is something I've always done through all my astronomy activities, is try to get to know the characters. And even beyond knowing the characters, one thing it's been almost impossible to find is to find, especially of these earlier double star, and we really haven't gotten to yet, but the William Herschels and the John Herschels, to get a sense of how they went about their business. There's so little written in the documentation, and there's just bits and pieces, and this is something certainly from just an astronomer, just an interest in astronomy. I think it's marvelous to find this kind of information out as to what they actually did and how they did it, and what they went through to get the information and the data that they did. So now, did I finish with Isaac? Oh, just to get on this bit of work about his work with the Mint. He personally did undercover work to build up cases against and prosecute 28 coiners and counterfeiters. These crimes were considered at the time high treason, punishable by hanging, then being drawn and quartered. So obviously, I mean, this is stuff I never knew about Newton, so I thought I'd share it. He was also a member of Parliament for Cambridge University and did 2 terms. So anyway, with universal gravitation, the phenomenon of double stars is about to take flight. Here we've got Struve 747, 752, and 754. We got one here. Well, there's one system here. I'm not sure where, and there's another system here, and I think this is the third. Again, the point of it wasn't to tell you exactly which ones they were. So. Christian Mayer, this is a character that I've never come across in double star until I started this research. So a Czech German astronomer and teacher of physics and mathematics, upon expressing a wish to become a Jesuit priest, a career choice not supported by his father, he left his home in Moravia and relocated to Mannheim. Again, all these guys are connected to the church. Mid-75th, Mayer is appointed the court astronomer at Mannheim. He publishes his catalog of double stars. And this actually is the first, and he called, the name of it is Discovery of All Hitherto Discovered Doubled, notice the D on the end of double, so doubled stars. So he was really the first person to put together a double star catalog, and a lot of it was based on stars that Flamsteed had recorded in his catalog. He'd just gone back and looked at them, noticed that they were double, and then just created a catalog. And this is how all the double star activity really began. It just, people saw these things, they recorded them. You had no reason to come back to them. They just, it wasn't until William Herschel discovered something later on his own, and we'll cover that briefly, very quickly. So available documents at the time would indicate that Mayer was the first person to explore the notion of binary stars. And binary stars are now what, when we talk about double stars, this is what initially people are thinking about, stars that are gravitationally bound. And that's what a binary star is. A double star may or may not be. Okay. So, but a binary star is. So Mayer is the first guy. And this is the first again, not until I started this research, and I mean, I've been around double stars quite a bit in the last 8 years. First time Christian Mayer even comes into the equation, so I was quite surprised. So this is really where it begins. Sir William Herschel, German-born English astronomer. Again, he was a pure amateur. He was a musical composer, is what he was, and the astronomy was something he did when time availed. Well, basically, the music was the daytime activity. The astronomy was his nighttime activity. So Herschel was an amateur astronomer since he had no formal training. He is without a doubt the greatest visual astronomer. Since he could not afford a good telescope, and in reality there was nothing of quality with high power, he began to construct his own. In his lifetime he built 400 telescopes ranging in lengths of 6 foot to 40 feet, and mirrors of up to 40-inch diameter. His sister Carolyn joined him in 1772 and was his constant companion. It is important to note that without Carolyn's assistance, his output for all his endeavors would have been greatly reduced. His favorite scope was his 20-foot, based on Newton's design, did not have a secondary mirror. So what, and I'll, again, after the presentation, I'll actually have a series of photographs I can show you later on of the actual telescopes and so on. So what he basically did, and you can imagine his 20-foot and 40-foot telescope. He was at the light receiving end of the telescope. The mirror was slightly offset down at the back end of the tube to direct the light up to the edge of the opening where his eyepiece sat. So he basically sat in the air, 30 feet in the air, most of the time, looking down the business end of the telescope, doing his recordings and so on. So again, this is kind of stuff, unless you get into these, getting into reading about it, you don't uncover it. And so this is what I found, especially on those nights when you can't get out and observe. This is great stuff to be reading about and understand and getting a bit of knowledge about. Okay, what can I tell you about Herschel beyond this point? Well, here's an excerpt that comes out of one of Herschel's, one of the many biographies. With the intuition of genius, Herschel, at an early period in his career, leaped to the conclusion that as a planet revolves around the sun, so in the regions of space, stars may revolve around stars, or sun around sun. It was a magnificent idea, apparently beyond proof, and would be reckoned at the time among the useless things of science. That's right. Yeah, useless things. So here he is early on. I mean, just one of these thinkers sitting there, and God knows what he was drinking at the time. But he said, why can't we have stars orbiting around stars? We've got planets orbiting around Earth, and of course, by this time, Newton's proved the fact that, and everybody understands that the planets are revolving around the sun. He's sitting there thinking, well, why can't we have a sun around the sun? And it's funny. You don't get in these early readings. Do you get any notion that people are actually associating sun with star? I mean, I've never come across. It'd be interesting to know where that bridge happened, where suddenly people started saying, those wee little things, well, that's the same thing as that star that I'm looking at, which is the sun. And I'm curious as to when that connection actually happened. I certainly haven't found it here, but this reading, the way this was written, just indicates that there really is, that connection just hasn't been made yet. So by 1803, Herschel is found, I've gotten ahead of myself. So anyway, Herschel basically did his first observations, his first 20-foot telescope, which was his favorite scope. He started using this in the late 70s, early 80s. Now, just to give you an idea of how people observed at that point in time, nobody had moving optics. In other words, nobody had German equatorial mounts. German equatorial mounts hadn't been invented. So the normal practice of observing is you basically, and part of this reason was because when you were doing this kind of research, you were also getting accurate readings. If there was something that came across your telescope, you wanted to be able to find it again. So basically what you had to do is you had to know what your declination angle was, and you basically had to be positioned at the local meridian and have it basically transferred to, in his case, well, he wasn't too far away from Greenwich. But the reality is the telescope had to be accurately positioned and basically frozen in place. And then basically he would sit at the scope and just let the sky roll by. So he sat there many nights, any night he could. He was out there basically watching the sky basically, and that's what all these astronomers did, is basically just go through the telescope. They weren't moving around, because if you look at some of the equipment they had, and you think of this 20-foot and 40-foot telescope on the scaffolding and everything else it was a feat just to get it accurately aligned and in place on an angle and then keep it there without moving and so on. So their observational technique was simply to sit there. So when something came through the field, he would call out to Carolyn, says, okay, and Carolyn had a watch or was in vision of a clock. He would tell her now has gone through the center of my field. So she would give a time. He knew what the declination angle of the scope was. He would do the math to basically back to Greenwich and so on. So at this point, he was able to establish that position so he could record it. So when he started doing these sweeps, this is when he came upon his first double stars. So he didn't go out looking for double stars. At no point, I mean, his concept wasn't, okay, I'm going to go out and research double stars. No, he just put his telescope in the air and just let the sky go by. So suddenly there are double stars going through his field of view. So he starts recording them. Well, he also recorded galaxies, globular clusters, all these other things. And we'll talk a little bit more about that later. But that's the technique that was used by most astronomers up until Struve, which we'll meet a little later on. Struve actually was the first one to get a German equatorial mount, the first one ever made. But in any case, that was the process that was used, and that's why all these things were just, you know, pure circumstance that they happened to come through his telescope when it was positioned there. So obviously, through the night he may adjust the position, may have shifted it 5 degrees or whatever, but the fact is, there was none of this moving around like we do your go-to, and no, that didn't happen. The telescope was put in place, and just you let the sky roll through. So in the early years, before his sister arrived, he'd just be, literally, he'd be at the telescope, and I don't think he was at a 20-footer at that point. He only had a 6-foot. But it would often be just discussion, some of the reading that he would you know, go out and do his observation, and then realize he's got to write some notes. So he heads into the house because of course no electricity or anything like that, no flashlights, no anything else. He went back in the house where the oil lamp or the candle was burning. So you wrote down your notes and you ran back outside. So obviously he very quickly found this was not a terribly efficient thing to do. So. And I'm not sure that he asked his sister to come or whatever, but in any case, this is how this relationship really developed. Like these two people were virtually inseparable since she came to England from Germany. So in any case, she became the recorder. She's also did quite a bit of observation too, has discovered comets and so on and so forth. But the point here is right now was first just to simply quickly discuss the notion, why did Herschel look at double stars? Well, he only looked at them because they happened to be sweeping through his telescope. So he started recording them. So this is basically late 1770, early 1800s. So this is the first group, and he does, he basically observes with all these sweeps and everything that he's doing, he observes and records roughly 800 double stars. It's not until roughly 1803 he actually goes back and starts to look at some of these double stars that are there. Strangely enough, 5, 6, 7, 10, 12, I'm not sure how many exactly, but he notices that things look like these things are working around each other. And again, because of not having go-to capabilities, you had to set up, and a lot of these doubles may have appeared on the same sweeps. So you can just try to think of how he would go out and set himself up for a night, especially if it was a 20-foot telescope. You saw the 20-foot telescope; it's on basically an A-frame kind of pier on pulleys, so this thing is not very movable.
So he's seeing the change in position angle.
He's actually seen changes that are alerting him to the fact. He's seen, and I guess he's observed them again for 3 or 4 times, because in those early observations, some were observed once or twice, others were observed more frequently, and again, it's sporadic because there was no double star science at the time. So he was just, from his own curiosity, looking at these things. So he revisits these things back again in 1803 and notices things are changing. It looks like they're rotating around each other. So sure enough, and it eventually becomes proof that in fact, he continues to observe these stars that he suspects are actually revolving around. And sure enough, he's able to prove the fact that they are in fact gravitationally combined. So at that point, that's where double star astronomy just jumps into full gear. Is that basically around the turn of we reach the 1803, 1805 period. So that's when double stars really takes off. And it's simply by a chance off. If he hadn't gone back and looked at those things again at that period, who knows? It probably would have been, 20, 30 years later on that somebody would have done the same. So when he learns of this, and of course the general astronomic community finds this out, suddenly everybody goes, wow, gravitation, stars revolving around stars. So every astronomer now is suddenly saying, okay, gee, I've got to start following these things. So again, the momentum just builds. Anybody in astronomy is now revisiting these things, and this was the importance of these catalogs. And if he hadn't recorded them, that information's not there. It's gone. It's whatever. So it's just this happenstance of just having recorded these 800, finding several later on, 20 years later, that there's actually some activity to say that these things are actually moving around each other, and leads to one thing after the other. Anyway, I'll give a little bit more on as a side for Herschel, just to interesting fact, just a comment that was made in one of the readings, says, but imagination sometimes realizes truth long before the facts of science make it known. Kind of an interesting quote. So in October 1983, a new 20-foot scope came into service for Williams. So this is where things started for him. It was in 1893. So that 20-foot scope comes into play, in which he starts doing these major sweeps. And if you know anything about the NGC catalog, the new general catalog, about 5,000 of those objects are actually first observed by William Herschel and then finally his son. So between the two of them, they catalog 5,000 of the NGC objects that form the NGC catalog. So it's just, again, and they were all through these sweeping actions. They were just, and again, the limited accuracy of the scopes at the time and so on, it's amazing that they were able to get the accuracy that they did, that you could go back and find these things again. So he builds his first 40-foot scope, 48-inch diameter mirror, and with an eyepiece it's said to have provided magnifications, I'm not sure if I can believe this, but 6,450 times. Pretty phenomenal.
How accurate was the mirror?
4 feet.
But how accurate would it have been?
Well,
God,
who knows? Who knows? In fact,
measure it.
yeah. Actually, a British astronomy group actually built a replica of his 20-foot scope, which was a 2-foot mirror, and did some testing on it. There's something I saw on the internet. I didn't do a lot of reading. The scope was basically the same, but the setup to turn it to the sky was not quite the same thing. It's quite a bit simplified. I'll show you a photograph of that later. Here's one story that describes William's driven nature. The story goes that he would be grinding mirrors and, wishing not to take a break, would have Carolyn feed him at the grinding wheel. It goes on to tell of one long grinding session that went on for 16 hours non-stop. So Sir William, I'm just going to go on this next slide. So here, what I talked about earlier, he discovers and catalogs 2,446 deep space objects, preliminary galaxies, and nebula. William, his son John Herschel, adds another 2,600. And basically, it's just, again, these are 5,000 objects that appear in the new general catalog. So he discovered 805 double stars, and again, these were recorded at the same time these other objects were being recorded in the sky sweeps. He built 400 telescopes. In 1971, he discovered the planet Uranus. In 1784, Herschel began systematically studying the shape of the Milky Way. He formulated a picture or a map of the Milky Way, which was quite remarkable in its time, and which even now is not wildly wrong. Interesting stuff. So anyway, his musical legacy, which really was his primary work, he composed 200 works, including 24 symphonies, 14 concertos, 30 sonatas for orchestra, organ, voice, and ensemble. It's incredible the capacity these people had. There's a Struve 546. Now, here's the thing that you'll find out, and this is one thing that Bruce McAvoy did after the first Cambridge Double Star catalog came out. He went in and actually, the Struve 546, it was actually Herschel's first observation. And unfortunately, the Washington Double Star Atlas catalogs it as a Struve discovery when in actual fact it was Herschel's. And the H is for Herschel. This Roman numeral 2, which is actually the Roman numeral 1 through 6, which actually defines 1 through 6 are different sort of groups of separations, 1 being the tightest separation and 6 being the widest separation. So in this case it's a group 2, and it was his 54th double star, so H2 54. Unfortunately, Struve gets all the fame. Okay. So anyway, now another thing of note, and again, I certainly wasn't aware of it, is he discovered infrared radiation. And I don't know, does anybody know about that experiment?
Yes.
Okay, so he was, and basically what he was doing, he had through a prism, the spectrum of light was, and he was just measuring the various temperatures. So he had taken the thermometer basically out of the path, the visible path of light, and was just had it off to the red end side just to get it out of the light path, so basically to get it acclimatized to the room temperature again before he went back and checked another temperature at another color. And suddenly temperature spikes on the thing. So with time, he finally realized, that's part of light, but it's the infrared which we can't see. So it was kind of interesting how that occurred. So just a simple, I have to put my telescope or my thermometer on this side, boom, infrared radiation. So interesting stuff. We'll move on. Sir John, English polymath, mathematician, astronomer, chemist, inventor, experimental photographer like his father. William Herschel, he was an amateur astronomer. Investigated color blindness and the chemical power of ultraviolet light. He instituted the use of Julian days and named 7 moons of Saturn and 4 moons of Uranus. During the years of 1821 through 1823, he re-examined, along with Dr. James South, who we'll talk about next, the catalog of double stars. The two of them basically went back and looked at his double stars again. And this would have been the third review period. There would have been a period in 1777 to 1880, 20 years later in 1803, and then 20 years later again. So those systems that were actually discovered or understood to be gravitationally bound would have had a third review in 1823, or that period from 1821 to 1823, and by this time by William's son John. So Sir John Herschel had 12 children, busy lad. He held a number of positions in the Royal Astronomical Society and won many prestigious awards, losing by a very slim margin an election for president of the Royal Society. The loss due primarily to an internal struggle between the traditionalists and the reformers. And of course, John was a reformer. And when he lost out in the election, he decided, I'm going to get out of here for a while. So he went to South Africa to basically survey the southern skies, and so on. So there's some interesting stories to tell about that. There was a geologist who was a member of the Royal Society, and this is again just in a biographical excerpt. The geologist, whose name was Lyell, last name, saw the irony in the fact that Herschel had done this work in South Africa because he failed to be elected president of the Royal Society. Lyell wrote the following: "Fancy exchanging Herschel at the Cape for Herschel as president of the Royal Society, which he so narrowly missed being. And I voted for him too." He says, "I hope to be forgiven for that." So ultimately what had happened is and all these discoveries of these 2,600 other nebulas and clusters and all these other things that were appearing in the NGC catalog because of his time in South Africa, had he won this election to be president of the Royal Society, he never would have gone to South Africa. So it's just strange how some of these things happen. Herschel was a scientist by nature, not a businessman, and after difficult years, frequently separated from his family by the demands of the job, which he tried his best to do. He resigned, and he resigned. His health had suffered through the stresses of the post, and it must have been come as a great relief to him to be free of the problems. He essentially retired to Collingwood at this stage in his career, being 63 years of age. Now here's the important part. To say he retired needs, of course, to be qualified with the remark that throughout his life he never held any paid scientific post. So all the science he'd done, and it's not just the astronomy. When he was down in South Africa, with the family and his wife and so on, his wife was an extremely gifted artist, and had done, while down there, he'd done 123 beautiful sketches of flora and fauna of the Cape of South Africa. So it's and there I'll read on further. He has an encounter with what's his name? So look at the next one. Yes. Oh, Charles Darwin. And that'll come up. So anyway, let's talk a little bit more about Herschel and his later years. So in late '83, Herschel and his young family arrived in Cape Town, a 20-foot telescope in tow. He moved to South Africa, and in as much as an opportunity to get away from the pressures and politics of science community as a chance to further the scope of the deep sky survey of his father. While in South Africa, Sir John catalogs a further 2,600 deep sky objects, as well as a significant volume of the 5,617 double star systems attributed to him. So in 1835, he observes the return of Halley's Comet, and the records would indicate that during these observations, Herschel determines that there is a repulsive force that is exerting a force on Halley's Comet, which will be later determined to be the solar wind. Neat. He also made the significant discovery that gas was evaporating from the comets. Just again, pure amateurs, you know, and just from careful observation and having probably still the most powerful telescope at the time didn't hurt either. So his wife Margaret was a talented artist. Together with she and John produced 131 beautiful color illustrations of the flora of the Cape. During this period, he has a chance encounter with the ship HMS Beagle and spends some time with Charles Darwin. It is a curiosity as to who inspired who to complete the illustrations of flora. If you look through some of the works of Charles Darwin, again, it's almost if you were to take the images you saw, or the prints of the sketches and stuff from Charles Darwin, and was produced by him for his books, and what you saw from Herschel's wife, look exactly the same. So you're not sure at this point, and I suspect a lot of that influence actually came from Herschel and his wife, and on the was transferred to Darwin, and you'll see a little later on in some of the readings here that I have. And then, okay, just as far as I guess, okay, so. Just again, going on to this notion of being retired, he certainly did not retire from scientific work, but free of the huge demands of the job of the Mint. Again, he was employed by the Mint as well, like Isaac Newton, strangely enough. I'm not sure the connection there. But anyway, for which he apparently had a fair salary. So again, he didn't need his science it wasn't a living for him. So the science was basically a pure hobby. He was able to complete many tasks which he and his father had started but had never reached completion. As Tate wrote, every day of Herschel's long and happy life added its share to his scientific service. Although he made no major breakthroughs for which he is remembered today, he was considered by many of his contemporaries as the leading scientist of his day. Bayet considered him the natural successor to Laplace when he died in 1827. In an obituary, it is remarked, "In John Frederick William Herschel, British science has sustained a loss greater than any which it has suffered since the death of Newton, and one not likely to be replaced." So obviously, I mean, again, here an amateur astronomer, basically an amateur scientist, has basically provided that much impetus to the scientific community. So it then goes on to say further that the article, in terms of the obituary, talks about, then goes on to say that even higher value than his research was the influence of his teaching and example in awakening the public to the power and beauty of science and stimulating and guiding its pursuit. Have a discussion, oh, that's my notes to me. So anyway, there was one particular item here. Oh, okay, there's a section here I missed. Did anybody ever know about the Great Moon Hoax? 1835. New York Sun newspaper wrote a series of satirical articles that came to be known as the Great Moon Hoax, with statements falsely attributed to Herschel about his supposed discoveries of animals living on the moon, including bat-like winged humanoids. No, there's one.
That wasn't true.
Fake news.
It wasn't true. Fake news.
Did they make a movie of it?
Jeez.
So anyway, Darwin made a comment, and I think it's a good indication of how much impact John Herschel had on Darwin and that short period of time that they saw each other in South Africa. And Charles Darwin writes, to throw some light, how did I miss this? Later on, Darwin would be influenced by Herschel's writings in developing his theory advanced in The Origin of Species. In the opening lines of that work, Darwin writes that his intent is to throw some light on the origin of species, that mystery of mysteries, as it has been called by one of our greatest philosophers. And of course, he was referring to Herschel at the time. So it's amazing what the connection these guys have with some of the real bright minds of the time. The best indication of his importance to the science community and to England in general is the fact that he's buried at Westminster Abbey. Anyway, we'll carry on. Sir James South, amateur astronomer in the 1860s, he relinquished he was actually a surgeon, that was his primary goal. He married into money, so he gave up the medical practice and just took up astronomy. So he was a founding member of the Royal Astronomical Society. South is best remembered, again, another interesting story about South and Edward Trofton, who was a renowned scientific instrument maker. South had acquired what was at the time the largest achromatic lens. It was a 12-inch lens that was made in France. And so, made by Robert Alguet Cachois. So, and he basically hired Trofton to build a mount for it. And anyway, South was never satisfied. He refused to pay Trofton, so Trofton finally took him to court. 8 years of court battle, finally awarded Trofton full price of it. So South was so infuriated with the legal result that he basically destroyed the mount, got rid of the telescope, and that was it. So that was pretty much the end of it. He does go on to do a little bit more astronomy or double star work in Paris 20 years later, and it's really probably just a reason to get away from all of the nonsense that happened around his telescope and mount. So this is a South 550, and the S is for South, James South. So, after 7 long years, the court battle went on to like the battle taking its toll, so James South lost his enthusiasm, his astronomical work went into decline. So he published, after he completed those 805 double star reviews of William Herschel, he did that with John Herschel, so that was a period of 21 to 23, and then later on in 1835, with a second catalog of 458 double stars, of which 160 were new discoveries. This was done in Paris.
So, Chris,
Yes.
this is what all right, so in order to determine whether two stars are double stars, you need to determine if they're gravitationally bound, right?
No.
Oh, you don't.
Remember what I told you about the WDS?
So it's still
As
not
long as it's in
gravita-
the catalog, it's a double star.
Well, okay, but that's
Okay,
just an
no.
artificial thing. I mean, that's
No, I know,
ridiculous.
but you have to remember, double star is just that. It talks nothing about
Right.
the gravitation. Binary star is what talks about the gravitational. There are all kinds of different stars that are actually gravitationally bound, and there are visual ones, there are
But doesn't it
non-visual
take a
ones.
long time to observe these binary systems to determine
Some
that
are,
they're...
some are very fast, and
that-
others take thousands of years. Some take 40
Okay.
years to cycle.
Okay.
They're again, if you get on the Washington double
Hmm.
star, the United States Naval Observatory website, where
Yeah.
you'll find the WDS. They also have, there is also what's called the orbital catalog. There's a catalog of roughly 1,100 double star systems where the orbits have actually been calculated.
Okay.
There are far more of these, but these are
Alright.
ones that have actually been calculated. And
Okay.
in there you can get a sense of, like, I mean, the range is from,
So
you know,
we're
a
still
matter of...
so we talk about discoveries, but just talking about visual, you know...
Yeah, early on, it was purely just finding stars that were in close proximity to each other. And that's all double star meant. So through the years, the connotation of double star has taken on a whole new kind,
Okay.
and that all resulted as a result of this gravitational discovery and so on. So, but still, when you talk about double stars, as I say, when you say double star, it's only a double star if it ends up in the catalog. In the Washington double star, you can't refer to. I mean, you can refer to two stars side by side as two stars, but you can't call them a double star system
Yeah, but
because
the
they're not
criteria
cataloged.
for
Yeah.
putting it in the catalog is...
Well, we'll get that's
All
coming
right,
up. That's
all right,
coming up.
all
That's
right.
coming up.
Chris, your middle sentence of your second paragraph there
Oh, back
is really quite remarkable.
this one.
458 double stars, of which 160 were new discoveries. We're talking the first half of the 19th century. If I would actually look through my telescope and think, hey, I think I've discovered something, I'd go to my computer in about 5 seconds, I'd find out from all the catalogs sitting on my hard drive whether I was just looking at something somebody else had found. We're already at a period where there are catalogs of 5,000 double stars already recorded. So if somebody actually thinks they found a double star one night in 1835, they've got to go through by hand all these catalogs in order to find out whether they've actually...
There's a huge amount of duplication going on
Okay.
in these early years, for the obvious
They
reason.
just weren't going through these catalogs. And
No.
Yeah, okay.
Well, let's move on just on that subject. So here's probably what we might define as Mr. Double Star himself. Okay, this is really and primarily it's because he's the first one to get an equatorial mount. Okay, he's got the best apochromatic optics that was made for the time by Fraunhofer. So the best glass that was. So he becomes the premier. And what he starts doing, he just starts in Herschel's catalogs and just starts going through. And that's why when I showed you earlier, he gets the credit because it ended up in his catalog, but it was Herschel that discovered it. Okay, so I mean, many places that have, and Bruce McAvoy has actually gone back and rebuilt the original 805 because basically it had been lost. Okay, there was really no record of it. So, like I say, this 805 showed up in Struve's catalog and in a variety other. Bruce finally went back and sort of said, "Okay, I'm going to rebuild his catalog." And on his website, he actually has the full catalog of Herschel systems with their full designation through the 1 through 6 designations. So, Frederick George Wilhelm Struve, German-Russian astronomer, started his studies in philosophy, but very quickly took up his passion for mathematics and astronomy. Prior to defending his doctoral thesis, he was given the task of installing the astronomical equipment in the newly, in 1810, constructed observatory at the university he was studying at. Within 2 years, was named its director. His first works, as was the case for most observatories of the time, was the accurate mapping of the stars. Double star astronomy was still secondary to his. Struve was a surveyor. He basically surveyed the meridian through the Tartu Observatory basically from the Arctic Ocean through to the Black Sea. That's what his paying job was as a surveyor. So all the double, and I mean, obviously he worked at the observatory too. But again, the activity astronomy was totally secondary to the business of the day, which was getting star charts for navigation purposes and this, and plus the surveying aspect of it. So again, these early astronomers held much different roles than what you'd expect of the time. So the years from 1850 to 1852, Struve was engaged in the surveying of the meridian that ran through the Tartu Observatory, a total length of 3,000 kilometers. That's a heck of a lot of surveying, a heck of a lot of time spent in the field, extending from the art and so on. And basically the accuracy is plus minus 12 meters. That's pretty phenomenal when you think about it with the equipment of the day. Struve was married twice, and the children numbered 12. Plus he had four nephews that he became responsible for. So he basically had 16 children. And he homeschooled them. He was instrumental in doing the homeschool. You wonder where the hell these people found the time. You know, there was no electricity either. You know, so it's phenomenal what these people were able to do. So in 1822 was one of the 3 astronomers to measure stellar parallax. Now, I should jump back. Herschel, the one thing that Herschel was trying to do with his double star observing was actually trying to establish stellar parallax. He had some success, I believe, on 1 or 2 systems to actually do measurements. But again, the equipment of the day just didn't allow a precise enough measurement for parallax. Struve was one of the first to be able to do that. So let's just get a little more on Mr. Struve. So astronomy, surveying, and navigation were inextricably tied together throughout this period. Astronomy took a back seat to both surveying and navigation, since the latter two were critical to trade, commerce, and building empires. Okay. So it just goes on to say, Struve was aware of double star work of Herschel and became very interested. So it wasn't until he started reading about Herschel's work that he even became interested in double stars. So again, it's amazing the interconnection, and it's just the how things sort of fell into place rather haphazardly. I mean, it was really a new science at the time. In this case, we've got Struve 761, 762. That's this group, and then here. You might recognize this little arrowhead of stuff. This is just west of the Horsehead Nebula in Orion. So next time you're visiting the nebula, you can, and this is fairly obvious. This is actually almost a naked eye target just below. Which is the star on the bottom end of the belt of Orion? Is that Mintaka? Oh, I don't feel so bad.
Yeah,
Nobody can name it off either.
Okay.
Zeta.
Yeah, anyways, if you just go straight down below that, you'll see this quite easily. And if you put your telescope on it, that's what you're going to see. So, so he closely follows the work of Struve, and in a lesser degree James South. Much of his early work involved the remeasurement of Herschel's systems that showed strong gravitational influence. Okay, so that's what intrigued him most, and so of course he built on that, and of course a large part of his own discoveries. So in total, may come a little later on in another slide, but Struve has attributed, there's about 3,200 systems that are attributed to Struve. Probably 400 of those are probably Herschel systems to which he's been given credit for. So, but anyway, a very significant and extremely well documented and properly measured stuff. And that's all primarily because of the equipment he was able to get. It was basically the Tartu and Pulkovo observatories were basically the best observatories of the time, of the era. They basically had the best telescope equipment up until the late 1800s, beginning of the early 1900s. So you can see the range of refractors, the 9.5, 15-inch Mertz and Alvin Clark 30-inch, which went in 1885. So again, simply because of his height, having the best instruments available to him, he became the premier double star observer of all time. His major publication title, Stellarium Duplicium et Multiplicium Micromatricia, contains the micrometric measurements of 2,714 double star systems. So the Washington Double Star Catalog contains about 3,200, and they have basically the prefix of STF or STFA and STFB. STF is his first catalog. The second one is a sort of an addendum, and B is an addendum as well. So here are other notable double star observers: James Dunlop, Otto Wilhelm Struve, who was a third son of Wilhelm, Frederick Wilhelm Struve, Sherburne Wesley Burnham, Reverend Thomas Espin, Bill Hussey, Robert Grant Aiken, Robert Jonquier, Willem van den Bos. A few interesting clips on all these guys, just a brief paragraph. Again, these guys are all amateurs. So James Dunlop, Scottish astronomer who cataloged some 7,385 stars, of which 166 were double stars. Otto Struve was the third son of Frederick Struve, who followed in his father's footsteps into the family business and became the director of the world-renowned Pulkovo Observatory at St. Petersburg, replacing his father. Besides double star work, he also pioneered solar observation. S.W. Burnham, Sherwin, Old Eagle Eyes, as he was described. He was so often referred to as Old Eagle Eyes. Another amateur astronomer who earned his bread and butter as a court reporter. He taught himself shorthand in his spare time he was spent observing and measuring double stars. He spent 4 years as a paid astronomer, and that's in his entire life. It was 4 years as a paid astronomer. And basically the years of 1888 to 1892, and that was at the Lick Observatory. Of course, he had the 36-inch refractor. So basically, and this is something I found out going through, and every time I came upon a Sherburne Wesley Burnham double, it was always tied up with either a Struve or something else. What Burnham did, he basically went in through all the old catalogs and started hunting for dimmer companions of the previously discovered pair. He basically went in and started re-examining these and finding many third and fourth companions of much dimmer brightness. So it was funny to see how that sort of developed. Now with Espin. British amateur astronomer, his primary occupation, he was a minister in his church. In 1988, he became vicar of town law and held that post till his death, a total of some 46 years. He completed a double star catalog of 2,500 systems, and in his early years, he had scoured the heavens looking for red-colored stars. So again, he was cataloging carbon stars. Well, he probably didn't know that. Well, he didn't know they were carbon stars. He just he saw red ones, and so he was cataloging. William Hussey, best known for his work with very close double stars. He observed and measured all of the Otto Struve doubles 3 times. He was extremely efficient. He made 1,920 observations in 1 year with a recorded 80 observations. It's not just observations, it's measurements, okay, in one night. By the time he ceased his double star work in 1905, he had cataloged 1,327 close binaries. Robert Grant Aiken. As with so many of the previously mentioned astronomers, Aiken was educated in mathematics and with an obvious interest in astronomy. He was offered a position as assistant astronomer at the Lick Observatory, and along with William Hussey, began his double star work. Together they cataloged the previous mentioned 1,327 close binaries. When Hussey left in 1905, Aiken continued his work on and added 3,100 more systems to that list. Robert Jonquier, French astronomer. total amateur. His family was in the textile business, and so that he, with that certain wealth, he was able to actually outfit and build his own observatory. He was a self-taught amateur who actually built his own observatory. Total of he actually built 2. During the First World War, he was exiled to England, where he was allowed to access the Greenwich observatories. He returned to France after the war to find his observatory destroyed. He eventually found work in the Marseille Observatory. In total, he had cataloged 3,350 double stars. Willem van den Bos, Dutch South African astronomer. He is recognized as the most prolific double star observers with 71,929 observation measurements, with a list of 2,895 new double star discoveries. And this was all done at the Union Observatory in Cape Town.
But he's looking at a different sky too, right?
Yeah, absolutely. But it's just the sheer volume of
Sheer
work,
volume.
just incredible. He worked out the orbits of 100, this is the key thing here, he worked out the orbits of 100 binary stars, and basically was recognized the leading authority in their determination. In fact, his method of determining orbital patterns is still used today. So, what constitutes a double star?
2
Well.
stars apparently.
2 stars. So basically, it still has to be in the WDS. So that's HJ 2695. Let me kill this for a moment. Boom, that's a lot better. So not a double. There's a dim and a bright. So that's not a double. There's another bright and dim pair. That's not a double. So again. And it's not to say that these couldn't eventually be doubles. Somebody's got to go in and basically determine that they're actually gravitationally bound before they're going to get included in the double star catalog. So anything that was in the old catalog, see the Washington Double Star Atlas, our Washington Double Star catalog, basically began in roughly the 1930s. The U.S. Naval Observatory basically took on itself to take all the double star catalogs and amalgamate them and bring them to one location. And basically, that's why I say that if it's a double star, it has to be in that, because it's taken all the old catalogs, put them together. And in reality, the WDS is more a historical document than an actual catalog of true binary stars. But it was never intended as a catalog of binary stars. It was intended and developed purely a way of getting all the records together in one place so that they could be maintained. Okay. So the thought thing is one can easily say, well, shit, why are clusters, globular clusters, called a double star? I mean, they're gravitationally bound, they're all sort of conglomerated together, but they're kind of outside the scope, and really the type of true binary. Well, you could say the Milky Way is a double star, because we're all sort of loosely tied together, but the reality is that scale and scope is far too large for the purposes. And really what double stars is really all about is learning about stellar mass. Okay, it's only through having gravitationally bound stars can one actually calculate stellar mass, and that's simply because of Kepler's laws and so on and so forth, and Newton's laws of gravity. That's the only way you can discover mass, and that's why double star research is so important, because it has allowed us to actually establish masses of things way beyond our immediate area. So next. So discover codes. So basically, you get a series, and this is a short list of a much longer list, but these are the ones that you're going to most often see in the Cambridge Double Star catalog. Is Burnham, Argelander, B for Van den Bos, A for Aiken, Dunn for Dunlop, ES for Espen, There's Herschel with his H1 and H through, so H1 through H6, HU for Hussey, J for Jonquière, HJ for John Herschel, STT for Otto Struve, STF for Frederick Struve. The STF A and B are actually supplementary catalogs, they're just additional catalogs to the original. And SHJ is for combined or observations that were done by James South and John Herschel, so they're basically designated an SHJ. And the WNO is basically a U.S. Naval Observatory double star. And most of these are actually double stars you wouldn't be able to see through a telescope. They're basically spectroscopic double stars. And so that's basically how things are labeled. You get a discoverer and you get his number. This is basically the sequence within all of Burnham's double stars. This was the 1300th and 37th discovery or catalog star. So in the beginning, when it was only 2 stars, we basically have an A and B, primary and secondary. And this generally, and if you go through the catalog, still generally adheres to this, like the Washington Double Star catalog. The primary is the brighter of the 2 stars. The secondary is the dimmer. Of course, there are exceptions. You'll find them in the catalog, but suffice to say they are there. But generally speaking, when you're talking about a primary, it's A and B. A being the brighter, being the dimmer. In this case, it's HJ 3945. So here are some of the common visual patterns. And this comes from Bruce McAvoy's site. It's called Astronomical Files from Black Oak Observatory. If you just type in Bruce McAvoy in your browser, it'll bring you right there. Probably the first or second one. It'll bring you to his website. This is a diagram from his website. So we've got a matched, and these are basically equal types. We've got a giant type and which would be this primary. This might be a smaller, denser. This is unequal mass, one being brighter, much brighter than the other. Signifies a potential unequal mass. You got a double single combination where these two are sort of doing their own thing together, and basically these two and this one are sort of probably rotating about a point there. Then you'll get double doubles. And of course, we've got epsilon A and epsilon 1 and epsilon 2 in Lear, the famous double double. There are all kinds of double doubles out there, and there's actually another one very very close to what we know as the double double, which actually I like more. It's a lot easier to separate. And this is what's called a fragile or common proper motion pair. And you'll find, when I showed you early on that Stella Dopey site, where they indicate the nature of the double star system and whether it's gravitationally bound or not, it'll say it's uncertain. In many cases, it'll say that it's not a gravitationally bound. A lot of the notion of being gravitationally bound is hinging on this common proper motion. So there are a lot of the satellite surveys that have been done through the last 20-25 years are now doing a lot of that proper motion surveys of all stars. And that's one thing about the Aladdin star site. And again, it's something that I think might be a good thing to do at a separate workshop in a small sort of work, 6 or 8, 10 people, if they're interested, to get together around a table and actually see how it's done. But there's an incredible amount of information on that Aladdin website from the University of Strasbourg, which will show that proper motion. So anyway, here we look at the position angle, and which is the position of the secondary in relationship to the primary. And it basically starts at 0, and depending if you're using a naked eye or you've got a setup in your telescope that will actually, like a prismatic reflect, which will give you an erect image field of view or view in your telescope, then you're actually measuring the angle in a counterclockwise rotation. If you've got a diagonal in your telescope, you're going to be measuring it in the other direction. Position angle is going to be measured from the north in a clockwise motion. So we're starting at 0 here, 90, 180, 270, 360. So 360 isn't used as 0, or 359 plus sort of thing. So that's position angle. So, and that basically is defining the separation between the stars. And that's how you would refer it when you look at and of course, you got to remember, I've kind of broken down. In my observing, I do everything with a erect image prism. It's image diagonal. It's just easier. And there are good prismatic erect image diagonals out there, and it just makes reading star charts and everything else so much easier. Yeah, I have to admit I'm lazy. I'm getting old. I haven't got time to try to figure out what this star chart means backwards, so I'm just making it easy on myself. It really helps in double star work too. Oh, should I go back? Is anything up? Okay, the information up above is just what I described, I think. Yeah, no, nothing new there. So, this was that image again of that system below the belt of Orion. Horsehead Nebula is over here somewhere. So that's 760, Struve 762. You can see AB is actually a very compact pair. My imagery couldn't separate it. So you're basically looking at two stars right there. The D, you can see the C component is very dim down here. There's the D and E, and you've got an H component over here. There's an I component sitting out here. Now, if we go into I believe I've got on the next I'll have the data. So 761 is here again. B and C are down here. A is up here. You sort of see this 1 and 2 combination that we saw in the previous slide. So here's the data from the Stelladopy website. So there's 760. So there's the AB, and so in fact, AB is actually AA and AB. So in fact, the A star is a spectroscopic binary. The B star, or the second star, is a spectroscopic binary. And so there's the AB combination. So in the case of AB, we've got a PA of 250. So in other words, so if we're looking at the AB, there's AB. Sorry for the shake. We look at C, which is down below, and it has a PA of 237. So up and down is 180, so we swing this way, so C is more or less in the position. So that's the position angle 237 for where C is in relationship to AB. So that's what this is trying to tell you. Its separation is 11.6, and in this case the AB magnitude is 3.76, and the C magnitude is 8.79. I'm not sure why it doesn't. You should be able to see that, but again, it's just the resolution of the image, unfortunately, when it gets blown up like that. So there you can see the various designations. I don't know who NOI refers to. BU is for Burnham. And there's Burnham, as I said earlier. He had the big telescope, so he was able to go in there and see a 0.3 arc-second separation. That's pretty damn tight. Pretty damn tight. You're not going to see it with you won't see it with James's 18-inch either. That's pretty tight. So here's the Struve group. There's actually a later Struve, 3135, which surprises me a little bit here. It still has a discovery date of 1823. You'll find some real anomalies in here too. You'll find a Struve companion that has a system that has a date of 1950. And you'll realize, well, it wasn't Struve that observed it. It was observed by somebody. I'm not sure why but there's all these kinds of anomalies that happen in the catalog that can be a little disconcerting but a little bit confusing. So anyway, there you can see there's a series of people that have been involved with various. So you look at the E star; it's actually a very tight pair as well. Okay, that's this pair up here. That's what that's showing. It's again, it's got a point. Yeah, so it's a 0.3. Same as the AB pair. The EA and EB pair is a 0.3 arc-second separation. What's a little bit surprising though is that the magnitude is 6.6 for the E, and that doesn't sound right in 11.3. Anyway.
Are any of these pairs and pairs of pairs gravitationally bound with any of the others that we see there?
For the most part, because unfortunately I didn't have I just pulled out this data. I wasn't expecting those kinds of questions. I suspect in some cases they are, in some cases they aren't. And the only way to find that out is when I was back at the Stella Doppy's website, you can see where the listing was to get the record of each one of those individual ones. If you were to go in and select it, then you would get the information. It would tell you if it was actually gravitationally bound, or whether it was uncertain, or whether it was just declared that it was definitely not gravitationally bound. But the data is there. It's just that you have to go further into it. Here for this I was really just trying to give an introduction into this and some of the basic stuff. There's a ton of information here.
I guess you'd make some inferences though, like,
Oh, yeah.
like AB, you know, with the separation of 0.3, you know, more than likely, you know.
Well, and you look at the AA and AB.
Yeah. Exactly.
Zero separation.
Yeah.
Okay, there's the only way these things are detected are by light drops as you've got eclipsing binaries, or you've got spectroscopic binaries, and so on. So I mean, there's all kinds of stuff. A lot of this stuff is with sort of beyond the realm of us amateurs, but a lot of it still is within the realm of amateurs. And for a lot of this stuff, believe it or not, in spite of all the surveys that have happened, a lot of these magnitude estimates are still visual estimates. Now this is one of the things that I've been doing with my imaging, and after you do a few thousand of these things, you begin to recognize stuff real quickly, and I've been able to very easily and very quickly recognize. I'll go through. I'll take a photograph, and I'll have the photograph on my monitor, and I'll go look up the data on another monitor, and just sort of keep two monitors going, one so I can keep my image up and one to get at data, and I'll sort of see, geez, that magnitude doesn't look like my image, not even close. So, and as it turns out, it isn't correct. But the problem is that a lot of the new survey information that you can find on the Aladdin or University of Strasbourg website has not been transferred to the WDS, or the Washington Double Star catalog. So this is an area which, well, in my case, I've been working with a couple of new contacts. I've got a contact in Austria, John Nansen out in Oregon, actually, Steve Smith in Boulder, Colorado, and Steve McGee out in Maui on Hawaii. And we've been, it's amazing the network you start to establish once you get involved into this double star work, and it's incredible the amount of number of people you get to know and meet. So we've actually up to this point, I think we've gone in and done about 250 corrections to the Washington Double Star catalog. And a lot of it has just been generated from me looking at a photograph and saying, that information I'm seeing in the catalog is not right. So I'll go back in and go back to the Aladdin website, and I'll check it there, and sure enough. And then my contact in Austria, unfortunately he's in an area doesn't get a lot of good observational time. So he basically does everything now with remote telescopes. So he goes in and does a complete photometrics of the double star. Once I've identified, he'll go in and actually take brand new measurements with a remote telescope. So we do reports, get these reports together, and then we send them off to the JDSO, which is the Journal of Double Star Observers. And so we submit papers. And so, I mean, these are the kinds of things that there's tons of this kind of work that can still be done by us amateurs. And a lot of it's simply because they're just, the people that are maintaining the catalog, it's not high priority for the U.S. Naval Observatory to maintain and study. They depend on people like ourselves, amateurs, that are just interested in work to actually generate this new data. And a lot of this stuff, which is, you look at the astronomy surveys and things that are done, it's all computer generated. There's nobody looking at telescopes anymore. So all the original data, which was visual observations, for the most part, it can be suspect. And until it's observed in greater detail, it's, and only until it's looked at greater detail, new observations by people like myself and others who are interested, that these anomalies and inconsistencies are discovered. So anyway, I'll carry on. Lots of work. So back to good old NGC 126. So there's a list that belong to this one. You can see all the various combinations and so on. Again, I won't dwell on it, but a ton of information on the Stelladopy website.
I have a question.
Chris,
So,
there's
go
a
ahead.
question.
Sure.
Yeah, I wanted to know, so what is the average distance between two
There's-
stars that would be...
There's no average. I mean,
not for the double stars, but the one that are gravitationally bound.
oh God, I mean, it's all kinds of, there's no consistency, and a lot of it depends on the size of the star. I mean, smaller stars are in much tighter orbits, bigger stars are in wider orbits.
I mean, the magnitude, the order of magnitude would be like, I don't know, like 4 light years is something, or...
You couldn't say there's an average, and honestly, I don't know. I can't answer that question.
Sure.
But there really is no consistency to it. They're all over the map.
Because I wanted to know whether we could discover that actually we are part of a binary system.
Well, apparently, and I think it's pretty much
With
a
our
given. Our sun
next-
is an anomaly. It doesn't have a companion,
Okay.
where most do. Okay, most stars do. Our sun doesn't.
Okay.
Okay. So, why double star? Back to the same old thing. Okay, so what's in double stars? Well, from just a pure observational point of view, first of all, it's a challenge of finding them. Overcoming issues of stellar magnitudes. Now, if you can imagine, when you look at this pair here, nice separation, absolutely equal. Absolutely no problem differentiating this. Now, a star of that, which basically has virtually no delta mag, in other words, there's no difference in magnitude. Now, if you were to take something of that same proximity, one star is at a mag 4, mag 3, and the next star is at mag 10, mag 11, there's a good chance you're not going to see that mag 10 star. Okay? So these are the things that you run into when you're just doing your casual observing, is that, I mean, there are so many different situations for how double stars set up for themselves, is that, it really becomes a challenge to find a lot of these systems. And I think that's one of the really neat things about double star. And a lot of this is dependent on your sky conditions. One day you might see it, one night you won't see it. In fact, from minute to minute you might see a double, because again, it means a lot of these systems are just given the conditions of the night, of your own optics and so on. A lot of these companions are at the limits of observation of your equipment. So you've got things just coming in and out of focus. They're usually, with averted vision, you're only catching glimpses of it. So it becomes a real cat and mouse game, and that's really what it is. It becomes a real, it's a hunt, it's a challenge, and it's a great way of improving your skills, your observant skills. So basically, when you've got close proximity, one has to notch up the magnification and to get clean separations. And of course, as soon as you get higher magnifications, you get greater effects of poor seeing and so on. So it's trying to find that, every night you're finding a different sweet spot with your equipment. One eyepiece and one magnification may work well on that system one night, next night you can't even see it. with the same equipment. So that's why double star observing is kind of interesting, because it really tests your observing skills. So on the plus side, there are virtually no end to the objects available for observing. So it will greatly improve your skills as an observer in an incredible variety of shapes, colors, and groupings. Observing double stars, but for the very dim, is not affected by moonlight. I've taken a lot of images actually before and during moon events, and even at dusk you can take double star pictures. In fact, there's some benefit to looking at certain systems during the dusk, because what you eliminate is, because you've got that brighter background, you're eliminating the effects of the brighter companion, sort of washing out the dimmer companion. So, and again, it's an excellent way to hone your vision skills. And finally, there's real science to be done. And again, like I say, it's a question of getting yourself immersed into it. So this was my first double star setup. Kind of simple. I had two telescopes that I'd set up on a side-by-side. And if you remember my that first image you saw of the 37 cluster, which was flipped, well, that's why it was flipped, because I was imaging it through a diagonal. I quickly learned after the first night this diagonal notion wasn't terribly great, because the diagonal released, camera swung around. I nearly had a heart attack as the equipment went slipping around on the mount. Not fun. So I lost that diagonal probably the first night. And of course we got epsilon 1 and epsilon 2, which are Struve 2032, 2382, and 2383. This is the other double, and these are exactly the same image scale. So there's epsilon 1 and 2. This is the other double in Lyra. So this is my more typical setup now. So I have a different telescope, but everything is in line. I put a flip mirror in here so I can, it's tricky when you got a narrow field of view. You're trying to find a double star. So what I'm doing here is, with the flip mirror, I've got a fairly wide angle. Gives me a fairly wide angle setup so that I can at least focus. And of course, I mean, these are still pretty primitive telescopes or mounts, so they their accuracy in terms of point and get to where you want to be still has a fairly good range. So that's why I do this, so I can hone in and I can bring it into the center of the field. And of course, there's enough slump on this imaging train that unfortunately what I'm seeing in the center of my eyepieces isn't what the center of my camera chip is either. So I have to play around with that. But anyway, that's the setup I use traditionally. That's that's Nirvana, by the way. Just gives you a little better idea. Flip mirror. So here's some recommended online resources. Stelladopy, Star Splitters, John Nansen. This is actually a great place to start. John is an extremely good writer, very interesting style, really captivating. And basically what he does is he puts together 3 and 4 system observing sessions. He does up the full maps, does a little bit of history, does a little bit of description. It's a great place to start. Okay, and he talks a lot about the ways, just observational techniques and so on related to double stars. Now this is astronomical files for the Black Oak Observatory. That's Bruce McAvoy's website. Absolutely, I needed to be brief, because if you're really wanting to learn something, that's where you want to go. He really covers a lot of data, and Bruce is a purist. He basically wants the Washington Double Star Washington Double Star catalog cleaned up to be binaries only, gravitationally bound stuff, and so. It'll be interesting, to see his point of view and so on. Journal of Double Star Observers, a lot of papers. I've got 3 or 4 of them in there myself. So it's basically dedicated to publishing articles on all aspects of astronomy involving double stars. Again, there's papers on actually doing measuring techniques with basic cameras, that kind of stuff. It's again a wonderful resource for anybody that's interested in exploring more than just the observing part of it. And then Cloudy Nights has a great discussion group on double stars as well. So here are the basic books that I brought along. And since I've done this file, I've actually gone out and got the newer version, which was done by Bruce McAvoy and Will Terry. This earlier one had really quite a few mistakes. In fact, when I was at the Double Star Conference in Maui back in 2011 or 2012, Bruce was actually a presenter, and he actually went through this catalog and basically sort of demonstrated how inaccurate a lot of it was, and so on. So that's why you got together later on. And a lot of the inaccuracies weren't necessarily due to James Mullaney information, because James was just pulling the information from the WDS. Okay, so Bruce basically went in and basically said, "Look, we got to clean this up." So he went and did the second edition, much the same vein, but his group of 2,500 to 2,200 to 2,500 double stars are basically binary gravitationally bound systems. He basically wanted to and that's the difference between the two catalogs. And my favorite double star, it's Jupiter. This is Jupiter. But here's what I wanted to show you about this delta mag. This is a longer exposure, but it very quickly gives you can see the moon buried in here. Well, these are the kinds of things that happen when you're trying to observe double stars with large delta mags in close proximities. And this is why it's so challenging in many cases to actually find these companions. So anyway, there it is.
Thank you.
Thank you. Questions?
Well, I think a true double star is gravitationally bound.
Well,
And
absolutely. Well, that's
where I'm
correct.
coming
But
from.
again, you have to understand the history of the whole thing.
Sure. But otherwise, you're just looking at two stars together. I mean, you could look up at the zenith, and you can see many stars that look like double stars, right?
Yeah.
So I'll go back to Mike's question again, which is historically before gravity was understood, or even before common motion could be calculated, what was their criteria for deciding whether something should be recorded as a double star? It's the same sort of question.
There was no criteria because there was nobody that was there was no central agency.
Nice.
In general, then, out of the catalogs
good.
from the 17, 16, 1800s, what was the general separation? What were they choosing?
Well, in fact, Struve actually, Fred Wilhelm Struve had he set for
I
himself
always thought it was.
a separation, maximum separation
So
of roughly 32 arc seconds. That was his defining number. For him, anything above that, probably, but keep in mind, he was the first one that was really looking at double stars and studying double stars from that perspective. In other words, being gravitationally bound. Up until that point, the cataloging and the identifying of double stars was purely that. It was trying to identify things in the sky, give them a position so that somebody later on down the road could look at it. And when gravity was discovered, people finally said, "Oh, okay, I've got to go back and look at this thing again and see if it's gravitationally bound." So
Did they
that's how it
then,
developed.
Like now you meet, have a convention, would they have had 50, 70 years ago conventions of people getting together?
No.
No.
I mean,
Okay.
these people communicated by Pony Express and whatever, So it's communications were slow, and so a lot of this work was done in isolation. And again, when you think of, these double stars observers were no different than Tycho Brahe or Flamsteed. They were just creating records, literally creating, and that's all they were doing. They weren't saying, because they had no notion of gravity, so they had no reason. But when you look at something up there and it happens to be close in proximity, it's just in itself, it's a kind of a marvelous thing, you know? And especially when you don't, you don't, when you look at these double stars, you don't see all these Meg 15 and Meg 20 stars behind. You see nothing. All you see are 2 stars and a black background, and you sit there and say, shit, how could these things not be? But the fact is, a lot of them aren't. A lot of them are. But it's just when you sit there at the eyepiece and boom, the thing comes into view, it's like, gee, that's kind of neat. It looks.
Are there more double stars far away because they get closer as the further the distance? You know, so I just wonder.
Absolutely.
So when you get a more powerful
but of course,
scope.
but that's totally out of the range of observation, and that's where all these new satellite surveys are doing now.
Okay.
Okay. And of course, Bruce talks about it too, and he's sort of saying, well, look, something that far away is absolutely useless from the point of trying to study stellar mass. So he's basically saying too, look, I mean, we got to somehow, and that's, he's correct in that. But the reality is, the Washington Double Star Catalog was never intended and never conceived as the document talking about gravitational bound stars. It was purely started to bring all the research, all the catalogs, anything that had been done on double stars together in one place
Chris,
and
the
managed in one place.
technical term is, it was a data dump.
Is that what it is?
It's a data dump.
Okay.
General catalog.
Oh, data dump.
So Chris, are you still maintaining your Yahoo group?
Yeah, I am. It still goes on, but I need to find a better venue for it because Yahoo really is getting bad.
Yeah.
You can't do much with the photographs
It's Google.
anymore.
Are your posts coming through? Yeah,
Not Google,
I-
it's,
yeah, but people have been complaining.
Or the Facebook of Yahoo, yeah.
I've enjoyed your talk immensely.
A lot of stuff, unfortunately.
Learned a lot. Just before I get.
Can we turn up the lights? Just to-
I'm kind of downsizing a bunch of stuff, and there's a whole bunch of double star books that if anybody wants them, they're fine. If you don't want them, I'll take them back to our club meeting sometime in the future.
I'll certainly take anything if nobody else wants it. Now, mind you, I've got, this I have. This I don't, this I don't have. Oh, this James Earl, that's his earlier one.
One more question. You said sometimes when you're imaging your image a double star and then you find its magnitudes don't match what's published.
That's correct.
Has anybody explored the idea of